Hello everyone, this is lecture number 7 and today we are going to solve the classical wave equation for vibration of a string. So this is also known as the one-dimensional wave equation. So let's assume that we have a string fixed at both ends. Okay. So and the length is designated as x. So here at this end x is equal to 0 and here x is equal to L. The entire length of the string is L. And now if we pluck at any one point of the string, if we pluck and release it, the string will start to oscillate. So the string from its mean position would go upward and then go downward. So let's try to draw a picture of a vibrating string of one end. And at any point, say at any point of x or at any point of time t, this displacement known as the amplitude u, which is a function of both x and t. So let's write this thing. The u in terms is a function of u, x and t is called, it is the amplitude function. And of course, it's a dependent variable. And what is the independent variable here? Of course, x and t are the independent variable. Okay. So that means at different x and different t, u would vary. And u is dependent on x and t. And here there is another constant part that is called v, is the velocity. So the velocity stands for, it is the velocity at which the disturbance propagates along the string. Suppose here the disturbance is nil and here it is nil, and the speed the disturbance propagates along the length, that is L, it is called the velocity. So velocity of propagation of the disturbance. Okay. Now, when the string starts to vibrate, there are two boundary conditions. So let us write the two boundary conditions. So what are the boundary conditions? Of course, when x is equal to 0, so the amplitude u xt, it follows the boundary conditions that for when x is equal to 0 at any time t, this is 0, and also u when x is equal to L at any time t, this is 0. So these are the two boundary conditions. So now let's directly write the classical wave equation. So that means there is a partial differential equation already derived for this vibration of string, and the equation can be written in terms of double derivatives of two partial derivatives actually. So this is the equation and we call it the equation 1. So what is the significance of it? So uxx, it is the double derivative of u with respect to x, and utt is the double derivative of u with respect to t, and v square, 1 over v square, v is the velocity and constant. Or we can simply write this thing, that this means that the partial double derivative of x partial double derivative of u with respect to x is equal to 1 over v square double derivative of u with respect to t. Alright, so both are same, so we call them equation 1. So now the question is, how did we write this equation? So this standard partial differential equation has been derived in any standard mathematics textbook that I have already told you. So you can refer to the textbook and you can find this classical wave equation. Remember, these type of equations not only appear in case of vibration of one-dimensional string, but many other classical physics problem, this type of partial differential equation appears. So this is a second order linear partial differential equation. Okay. So now let's try to solve it. Okay. So I'm going to erase the board and we'll start. So here we go. I have written the partial differential equation. Now we are going to solve it. So we will follow the method of separation of variables. So this is a very helpful tool in solving such kind of partial differential equation. And in our quantum chemistry courses, not only such type of partial differential equation, but many types of Schrodinger equation can be solved using this method. So what is this method? So this method tells us that, okay, this, let's assume, okay, so uxt, okay, this amplitude function contains both the function of x and t. So let's assume that this function can be written as the product of two independent functions, that is the function of x known as the bigger case uppercase x and the function of t denoted as the uppercase t. So this uxt is actually the product of two functions that are independent from each other. And if we write that, then of course our boundary condition changes slightly. Means of course it is the same, but instead of uxt we can write x. So our boundary, since there is no boundary condition on time, we have only the boundary condition on displacement. So our boundary condition adjusts like this. So at x is equal to 0, x value is 0, and at x is equal to L, our uppercase x value is 0. So these are the modified boundary conditions. So what we do next, that now we replace this uxt with xx and tt here, and of course we have to take the double derivative of it. So remember, when we apply the partial derivative of this such kind of product, the other part, which is independent of x, behaves as constant. Okay, so let's write that, or by replacing uxt with this function, then we can write, that is this part stays constant. So every time I won't be writing the x and t within bracket, so I will directly write the t as the function. So t del 2x del x square is equal to 1 over v square. Now x remains constant, and del 2t del t2. Okay, so now what we do in the next step, that is that you see this has not been separated yet, so this part has t and this part has x. So we divide both sides by this function, that is xx and tt, the product of this. So, or we divide both sides by x and t, the product of x and t, or we get this 1 over x del 2x del x square is equal to 1 over v square, and then we have t multiplied by del 2t and del t2. Alright, so we can call it as an equations with separated variables. You see here this part only contains x, so this is the function of x only, and this part is function of t only. So we got our first success, that we were able to separate the two variables. So x segregated at one side and t segregated at another side. So the next part is this left hand function is only function of x and the right hand function is only function of t, and both are equal. So when it can happen? So when it can happen only when that the both of these two corresponds to something constant value. So let's say this is equal to k, a constant. Otherwise this condition can't be fulfilled. So now let's try to solve this thing, because this part is equal to constant and this part is equal to constant. We will try to solve this to figure out how we can solve x and t. So our target is to find out the value of uxt. So we are actually going to find out the solution. Okay, So this is our target. So that means we have to find x and t separately, and then we take the product and we get u of x and t. So question is how can we solve this? Okay, this is equal to t. The answer is at this point we are unable to solve it because this value k is an arbitrary constant, and from this information we have no idea what is the value of k. So right from this form we cannot solve it. So what is the way? We have to take the guessing game or the game of elimination. So that means we have to take some arbitrary possibilities of k and we will narrow down our options. Okay. So the first option, let's assume the simplest, that is k is equal to 0. So let's see if we take k is equal to 0, what would be the solutions look like. Okay. So let's check it out. Okay, so before we proceed further to solve these two set of equations, we separate them into two different simpler equations. So from this, we first write this as equation 3, and the second part with function of t is equation number 4. Now we can recognize that both the equations 3 and 4 are in the form of x double prime minus kx is equal to 0, and which you have already seen in earlier lectures. And I don't think you have any problem identifying such equation as a set of ordinary second order linear homogeneous differential equation. And now we know how to solve it. So therefore, so now it's better to assume that k is equal to 0. If we can solve the two equations, so it would give us x is equal to a1 x plus b1, and of course t as a function of t, of course, give us something like a to t plus b2. All right. Now both these a1 b1 and a2 b2 are known as the constants of integration. So now let's take a look at these two, and also you take a look at the boundary conditions. So if we apply the boundary conditions to get specific solution, so the boundary conditions tell us that x0 is equal to 0. All right. Now if once we put these conditions over here, x0 is equal to 0, then we get that a1 is equal to b1 is equal to 0. It has to be 0. So if both the constants of integration become 0, so we automatically get that x at any value of x is equal to 0. All right, for any x. Now if x for any value for x is 0, then of course this implies that the amplitude function for any value of x is equal to 0. So what does that mean? So that means this assumption that k is equal to 0 would automatically get me a solution, a situation where the amplitude function is 0 for all value of x. So that means what? So that means my string is not vibrating. So that means it is at horizontal position all the time. So what is that called? So this is definitely is a case of a trivial solution, and we have already seen that how trivial solutions appear, and this trivial solution is also a solution of the entire set that gives you a very basic condition. That means the string not vibrating, that means the string lying in equilibrium position is also a possible solution, but we are not interested in that because that gives us a picture that the string is not vibrating at all. So we discard this assumption, because this gives us a trivial solution. So that assumption that is k is equal to 0 is not good, and so we have discarded it. So we are left with two other options. So k can be positive or k can be negative. So let's figure it out. Our second option, that what if k is positive? Okay, so let's work it out here. So once again, let's try to solve the two equations by assuming k is equal to positive. So these are the two equations I have written once again. Probably last time I used partial derivatives of those, denotion of partial derivative, but these are simple ordinary derivatives, so uh, this d rather than delta should be used. So if I have used wrongly, it's some technical mistake, but there is no major problem on that. But anyway, uh, so how can we ensure that k is a positive? So we can only ensure a quantity is a positive if it can be expressed as a square of some real number. So let's assume that k is equal to beta square and beta is a real number. So if we try to solve that, so definitely solving equation 3, we straight away get that you are already familiar of it. So c1 e to the power plus beta x plus c2 e to the power minus beta x, where once again c1 and c2 are the constants of integrations. So now we have to apply the boundary conditions once again. Okay, so what are the boundary conditions? Then one of the boundary conditions is at x is equal to 0, this x is 0, means uppercase x is 0. So if we apply that condition at x is equal to 0, if we put x is equal to 0, this part becomes unity and also this part becomes unity. So we are left with c1 plus c2 is equal to 0. Okay, so we are left with that c1 plus c2 is equal to 0. And it also tells that x is equal to L is also 0. So if we put x is equal to L, it should be 0. So if it is, so that is only true when both c1 is equal to c2 is equal to 0. So whenever these two constants of integrations are individually 0, then these boundary conditions can be true. So what we find, once again, if c1 and c2 is equal to 0, we are left with no choice but xx is equal to 0 for any x. So that tells me that the amplitude function uxt is equal to 0 for any x. So once again, this is a trivial solution. Alright, and definitely that means the string is not vibrating and we are not interested to this kind of trivial solution at all. So we need to discard our second possibility, that is assuming k is equal to positive, it's again discarded because this gives us a trivial solution. So you see, now we are left with only one option, that is the assumption of k is equal to negative. So let's assume that and work it out and see what we get next. So let's try it out with our assumption that k is equal to negative. So then that means the k can be represented as the negative of a square of a real value, that is beta square. So or root over of k is plus or minus I beta, obviously we have seen it earlier. And then of course the solution for equation 3 can be written as something like this, c1 e to the power this plus c2 e to the power this, and we have already seen this, that an alternative form can be written as by trigonometric function of cos beta x plus b sine beta x, etc. So now let's concentrate on this format. And then let's apply our boundary conditions. Boundary condition says that of course x is equal to 0 is equal to 0. So if we put x is equal to 0 here, so this part becomes 0, that because sine 0 is 0. So therefore it tells us that for x is equal to 0, cos 0 becomes 1, so this becomes is equal to a. So obviously we find from the first boundary conditions, that is a, this coefficient becomes 0. So this tells us that xx is equal to b sine beta x. Alright, so now let's put our next boundary condition, that is at x is equal to L, we also have 0. So here we apply this value over here. Okay, so in which condition that, if we put that, so b sine beta, if we put x is equal to L, alright, L is equal to 0. The question is when it is possible, for what value of b or beta or L, whatever, this becomes 0. So one option, so we have the option 1. So option 1 says that this is true when b is equal to 0, but if we put b is equal to 0, then already a is equal to 0, so everything becomes a trivial solution. Okay? So of course, I have explained it earlier that why trivial solution is not wanted. So we cannot put b is equal to 0. So we discard this condition, that is b is equal to 0. So then what is left is what happens when sine beta L is equal to 0. So let's quickly take a look at it. So let's take a look. So far we have found that xx is equal to b sine beta x. So far this is the solution we have found, but we have also seen that a is equal to 0, but b naught is equal to 0, because b equal to 0 gives us a trivial solution. So on what condition xl is equal to b sine beta L is equal to 0, that, or in other words, when when x is equal to L, b sine beta Bl becomes 0. So we have already seen that b cannot be 0, so of course sine beta L has to be 0. The question is, when sine beta L is equal to 0? The answer is when beta L is equal to an integral multiple of pi in terms of radian. So n stands for 1, 2, 3, etc. positive integers. But of course, n cannot be equal to 0. Why n can't be equal to 0? If n is equal to 0, once again, what happens? That this entire part becomes 0. That means, once again, we have a condition for trivial solution. So, now we have seen how many times the trivial conditions for trivial solution appears. If you follow the lectures, then you will see there have been 4 times where I have talked about the possible scenario of trivial solution. So therefore, we now get beta L is equal to n pi of, right? So now we can find out the value of beta. So beta becomes n pi divided by L. Alright? So therefore, from beta we have already seen the value of k. We have assumed that this is negative of beta square, isn't it? So therefore, we also can find the value of k from here, that is negative n square pi square L square. So you see, by trial and error method, we can finally find the value of that constant k, which is this. Alright? So now let's come back to our complete solution. So our final and complete solution becomes something like that. That is the x part. So solution for x part. So this becomes b sine, instead of beta, what we can write? Yes, instead of beta, we can write this n pi divided by L x. Alright, so this is the solution for the displacement part, x part. So we still have to find out what is the solution for t, and then only we get our complete solution, that is u of xt is equal to this multiplied by this. Alright, so next we have to find out what is the solution for the time part t. So that we will find out in our next lecture, that is lecture 8. So till then, goodbye.